sort of talk in terms of the density of equations. Unfortunately, they're somewhat unavoidable in the things that I'm going to talk about. And so, this is interesting. Right, well, we just went through a whole lot of, oh, come on. Okay. Okay, so yeah, so this is joint work with Josh and Monte, and in fact, you know, Josh has been very much the main player in this, and in particular, most of the slides here I have to thank Josh for. So, you know, what we're interested in is, you know, we have a derived allele that's arisen sometime in the past, and then as, you know, throughout time, its frequency in the population has gone up and down until, you know, it's at some level at the present day. And with, you know, we're sort of interested in various things about the history of that allele, you know, the time that it first arose in the population, and, you know, to what extent it's been under selection, and, you know, to the things like the dominance coefficient. And if you don't quite remember what those things are, I'll sort of describe those briefly in a little bit. And the sort of data that we have is, you know, at a bunch of times in the past, we have, you know, samples of, you know, some number of chromosomes, and, you know, and in those samples we'll have some number of copies of the derived allele, and so that's, you know, some kind of, you know, we can think of it as an estimate of the frequency of the derived allele in the population as at that time. And of course it may be the case as here that we're sampling genetic material prior to the time that the allele arose, and of course at those times we're going to see the derived allele at zero frequency, and of course at later times, just by chance, we could also see it at zero frequency as well. Okay, and so just sort of let me remind you of the basic Wright-Fisher story that, you know, if you'd been good boys and girls and come to the boot camp, I wouldn't need to tell you this, but, and I probably don't need to tell any of you it either. But, you know, we just have the sort of basic Wright-Fisher story where we have two alleles, and then this kind of resampling mechanism that gets us from one generation to the other, and we have, you know, kind of fair sampling if we're in the neutral situation, but if there's some kind of selection going on, then there'll be favoritism of one allele over the other. And we're going to have this sort of general diploid selection model where, you know, this homozygote, you know, has fitness sort of 1 plus S, you know, compared to the other homozygote. And then the heterozygote has a fitness of this form here, okay? And, you know, if you just go through a calculation of how the expected allele frequency changes from one generation to the next, then you get kind of a rather nasty looking expression, and an even nastier looking expression for the way that the variance changes from one generation to the next. But, you know, up to kind of smaller order terms, it looks like this. And but we're going to think that we're in the world where n's very large, and we're going to sort of pass to the usual diffusion limit story that I talked about in the boot camp, where we assume that the population size goes off to infinity, and our selection parameter scales in such a way that 2ns goes off to a value alpha. And then we get this Wright-Fisher stochastic differential equation, sort of a drift term here that has all the details of the selection embedded in it, and then the stochastic term, or the diffusion term, that is just coming from the resampling and is unaffected by anything to do with the details of the selection. Okay, and so one can also suppose that population size is varying, and in such a way that on this diffusion time scale, so after 2nt generations, the population size is of this form here. So rho t represents the relative population size with time measured in diffusion time units. Then one also gets a stochastic differential equation in that limiting regime, and the selection looks exactly the same, the drift term looks exactly the same, but the stochasticity is changing, and so the larger the relative population size is, as we all know, the effect of the stochasticity will be diminished as it gets larger. Okay, so if we've got these sort of samples of ancient DNA, then it's sort of, if somehow we'd been actually given the allele frequency path, well, immediately we'd know what T0 is, right? Because we just have to see when the allele starts having positive frequency, and the two selection parameters, the selection strength and the dominance coefficient, those guys, would be inferable from the allele frequency path, because the likelihood of our data is just going to be a bunch of binomials. Well, for a start, we could, if we knew the allele frequency path, we could do all sorts of things to infer alpha and H, but if we also knew the allele frequency path, then the likelihood of the data would be just binomials that wouldn't depend on alpha and H, right, or T0, right? They'd be just things to do with the population frequencies at the time that we sampled. However, because we don't actually observe that likelihood frequency path, and so if we want, the likelihood of the data just given these scalar parameters, alpha, H, and T0, the things that we want to infer, then computing the likelihood is hard, because we've sort of got to integrate out the whole allele frequency path, this kind of infinite dimensional type object. And doing that is morally equivalent to solving a PDE that doesn't have some nice kind of closed form solution. And despite that, there's been sort of various attempts at doing this kind of inference. The earliest paper, I think, solves the PDE numerically. This paper here, of which Monte and I were co-authors, is doing a particular approximation to the PDE using birth and death processes, birth and death type Markov chains. And then I think the most recent paper in this area by Matthias Steinrücken and others, using orthogonal polynomial ideas to approximate, affect essentially the solutions of the PDE that come up from doing this integrating out the path type story. Okay, well, because of this fact that the likelihood of the data given the allele frequency path is, something that's easy to compute, a sort of a natural idea is to just take this unknown frequency path as, just yet another parameter that you have to estimate. Now that sort of seems, okay, well that's sort of a nice idea because now you've got easy likelihoods, but of course, this will only work if you've got a prior that makes sense, right? If your prior on the path is, that it's just a straight line with an unknown slope, well, that's got no kind of connection with, the alpha and the h that you're interested in estimating. So, this approach is really only going to tell you something if, you work with the right prior, and the prior should be such that, under that prior, the conditional distribution of the allele frequency path, given alpha h and t0, and, that you're seeing something that's an allele that's segregating at the present, is that, it should be what it is under our Wright-Fisher stochastic differential equation model. Okay, so, this is a promising idea as a way of, getting alpha h and t0 using essentially off-the-shelf ideas for doing Bayesian inference using MCMC type ideas. But it also carries with it a little bit of a bonus because it gives you some kind of an imputation of what the allele frequency path was, and that's something that we might be interested in, just for its own sake. Okay, and so as I sort of already intimated, the obvious way to approach this is, if we're going to be Bayesians, is to get, a posterior using some sort of MCMC idea, like Metropolis Hastings. And, when we sort of do Metropolis Hastings, we're just, because we're usually working with things like scalar parameters or, vector valued parameters, without even really thinking about it, we're always working with likelihoods, right? So we're assuming that, or densities, right? Another way of saying it, right? So there's always some reference measure in the background such that the probability measures that we're working with have densities against those measures, right? And of course, for vector valued things, it's usually just, Lebesgue measure on whatever dimensional Euclidean space we're working with. But here, the path is this kind of infinite dimensional object, and so we need to be working with some probability measure on the space of possible allele frequency paths where, we have reference measures that are useful for doing the kind of ratios in MCMC. Yeah.
Surely it's only relevant what the allele frequencies are at times you observe. So I don't see that the dimension is really infinite. Although there's an infinite path, you only care about the times at which you're observing.
Right, but we need the stuff. The whole thing is, if we only care about those things, then that's integrating the PDE, right?
But that's,
well, we don't want to do that. That's the whole point. We're trying to avoid doing that.
Well, I don't understand. We'll talk about it later.
Yeah. Yeah, I mean, mathematically that's true. That, the likelihood just involves, exactly those things, and then you have to worry about, what's the probability
Yes, of
that,
course.
right, and that's something that's nasty. Whereas this procedure actually solves the PDE for you without you noticing that it's happening, right? That's what's going on. This is doing, if you like, these infinite dimensional sort of, expectations of these functionals on an infinite dimensional space that you could solve the PDE to get, but we don't want to do that. And so it just automatically, MCMC automatically computes the expectations of these functionals for
We
us.
still have MCMC of the finite number of times that you care about, but we should argue.
Yeah, but you need to sort of write down likelihoods, right? And that's
You need to have
involves
transition
solving
probabilities
PDEs.
in continuous time.
right. So, we're avoiding doing that, right? I love PDEs, but, it's sort of nice when, you don't actually have to, think too much, right? Okay, so what do we gain? Just a little bit of stochastic analysis. So let's just use this notation here for, the distribution of a Brownian motion that's going to start at some time t star in position x. And now suppose we've got a stochastic differential equation that looks like this. The stochastic term, we just have a Brownian motion without any coefficients out the front of it. And then we've just got this time and space dependent drift term. Okay, and this classical theorem of Girsanov says that if we look at the law of paths that satisfy this SDE, then that probability measure is absolutely continuous with respect to the, where did I go? Absolutely continuous with respect to the distribution of the Brownian motion with this very nice explicit Radon-Nikodym derivative. And this is not all the way out to time infinity. This is, if we just look at paths that are over some finite interval from time t star up to t, that, this is the density of this probability measure here with respect to this reference probability measure. So we've got these nice explicit densities, okay, but there seems to be a fly in the ointment, right? That the Wright-Fisher SDE doesn't look like the sort of guy that Girsanov applies to, right? To which Girsanov applies, right? That, Girsanov is all about guys that are just, Brownian motion plus a drift. And here we've got something a little bit complicated out the front of the Brownian motion. So we'll have to do a little bit of pre-processing to beat things into shape where Girsanov will apply, and that's going to be just via a time and space transformation. And so the time scale is sort of something fairly obvious. We're just going to go to this new time scale here, right? Remember, this is the relative population size, and no surprises. This is what happens to the Wright-Fisher diffusion when we sort of stretch and squeeze time using this transformation. That we get a diffusion term that looks like just the Wright-Fisher guy with a constant population size, but then the stuff that's going on with the drift term that's encompassing the selection, that gets messed around a little. And the F inverse there, I just should stress, is not 1 over, but the functional inverse of this monotone function. Okay, so the space transform is somewhat cleverer, but fortunately somebody extremely clever, Fisher, had already figured it out for us. And so if you just transform the space variable, so use space, I mean the frequency the frequency variable, then using just Ito's lemma, you get this rather complicated looking SDE here with sort of rather nasty looking drift term, but the good thing is that we just have a nice unadorned Brownian motion for the stochastic term, and so Girsanov's going to apply. Right. So theoretically that's great, but we sort of had this difficulty that this transformed guy, space and time transformed guy, lives on sort of 0 pi, and of course it can go to 0 or pi, and that corresponds to loss or fixation. Whereas our reference probability measure is something about Brownian motion, which is just a process that freely wanders over all of the reals. And so what's going on here, the consequence of this is that this drift term here, I'm sure you see it automatically, right? It blows up when the variable here goes to either 0 or pi, right? You remember, right? Cot is, cos over sine, and sine of 0 and sine of pi are both equal to 0. So bad things happen as you approach the boundary. And so that's going to create a bit of a problem with densities blowing up when we want to infer allele age. So we need to have a reference measure that's something other than the distribution of Brownian motion, that's sort of more tuned to the problem that we're working with.
Steve?
Yeah.
Haven't you just completely screwed up the time scale? You don't know when the points were sampled, and you have...
No, it's deterministic, right? Because it's...
But it's been moved around by the time change, right?
Yeah, but the time change is a deterministic one. It's just using the population size. 1 over rho. Rho is deterministic. We're not assuming that...
Rho is known.
Yeah, we're assuming that rho is known.
Oh, okay.
Right.
All right.
Yeah. It's not something that we're inferring. Yeah. Okay, and so, now, suppose that we've got 2 of these SDEs that Girsanov applies to. Then we know that they've both got, their laws both have densities with respect to the law of the appropriate Brownian motion. And so, if you're just willing to sort of accept this kind of, heuristic little argument here, which you can actually make rigorous, you get that the law of the first guy has a density with respect to the law of the second guy, which is just, a ratio of Girsanov-y type densities. Okay, so again, something that's really, sort of nice and concrete and easy to work with. Okay, so now, we saw that, our time and space transformed Wright-Fisher guy, and we'll write this for its distribution, solved an SDE that just had an unadorned Brownian part, and this appearing in the drift. Okay, and I said this blows up as y tor goes to 0, and this is exactly how it does blow up as y tor goes to 0. And so when seeking a better reference measure than Brownian motion, it might be a good idea to apply this kind of story here, where the SDE that's giving rise to the new reference measure, the thing that we're going to put on the bottom here to get our density, is something that where the drift terms have the same type of singularity as y tors going down to 0, right? Because if we do that, then we're not going to have densities going off to infinity and creating problems in our MCMC algorithm. Okay, and so that sort of suggests that our new reference measure should be something that where the coefficient in the drift term has this kind of singularity as the frequency variable goes down to 0. And of course, well, we could just take Q to be equal to P, but the whole point is that we, don't know how to sample from things related to P easily. And so it'd be better to have, necessary for implementing something like Metropolis Hastings, to have something that we can sample from quite easily so that we can, do the whole story with proposals, etc. in Metropolis Hastings. Okay, so another little bit of stochastic analysis is, let's just sort of note something that, if I've got a d-dimensional standard Brownian motion, then because of the radial symmetry of this guy, if I just take the radial part of it, that'll be a Markov process in its own right. Normally when you take a function of a Markov process, you don't get something that's Markov. Here you do because of the radial symmetry. And the resulting Markov process, the resulting diffusion, is called a Bessel process of dimension d, and usually written that way. And again, if you apply Ito's lemma, you see that this guy satisfies a nice little stochastic differential equation. And this stochastic differential equation makes sense for all values of the parameter d that are non-negative, whether or not d is an integer, right? Of course, this definition here depends on d being an integer, but this SDE makes sense no matter what non-negative number d is, and so this such a process we'll call the d-dimensional Bessel process. And Josh did some nice simulations. So here's sort of the case d equals 2, where we've got a two-dimensional Brownian path, and then when we look at the radial part, we get a nice curve that looks like this, right? Which starts at 0 and then doesn't go back to 0 because as we know, Brownian motion will get arbitrarily close to 0 at times in the future, but never return exactly to 0. Okay, so let's sort of remember that when the frequency variable is small, the drift of our time and space transform right Fisher diffusion looks like this, and the zero-dimensional Bessel diffusion satisfied an SDE like that, and so we see that the singularities are matching up exactly in the way we want, right? So it looks like the distribution of the zero-dimensional Bessel process is a good candidate for a reference measure. But remember, we need a reference measure that's sort of something that we can sample from. And actually, before I get to that, let me just sort of mention one other point, which is that this consequence of Girsanov was that, if we've got, if we had our right Fisher guy, space-time transform right Fisher guy, and this was our zero-dimensional Bessel guy, then the density of this guy with respect to that is going to be given by this ratio of things from Girsanov. And so to compute this numerically, it seems as though you've got to do stochastic quadrature, right? You've got to numerically evaluate an Ito integral, and people know that that's kind of not a nice thing to do numerically, but there's a very nice observation that's been exploited quite extensively in the group around Gareth Roberts at Warwick, where, you know, they figured out that just essentially by a clever integration by parts type idea, you can convert these stochastic integrals into expressions that just involve, you know, ordinary, well, Riemann integrals. Okay, and so that's a kind of means that these things aren't as nasty numerically as you might think they are. Okay, but we've still got, you know, another thing to address, which is, you know, our space and time transformed Wright-Fisher diffusion. You know, if we start at, you know, exactly at 0, it's, you know, going to stay there. So will Bessel 0. It doesn't get away from 0. 0's an absorbing boundary point. And so, you know, because what's happening is that, you know, we've seen an allele that has escaped from 0. It's kind of done something exceptional. It's been lucky enough to, you know, be brought into being by a mutation in some individual and then make it to macroscopic frequency in the population. And so, you know, our prior will need to take that into account and put, you know, its mass on paths that actually start at 0 at some time in the past, but then manage to escape from there. And so, you know, I know we're piling on the stochastic analysis here, but, you know, we need a sort of another idea from stochastic analysis, which is this notion of an entrance law. So our Wright-Fisher guy, you know, because of us, you know, messing up the space and time scale, you know, it's a Markov process, but it's time inhomogeneous. It's, you know, the dynamics of what you do depend on not just where you are, but what the time is. And so, you know, this is, you know, the density against Lebesgue from going from position x at time s to position y at time t. And then an entrance law is, you know, sort of a way of getting the thing started from some time t star. And so it's a way of getting the thing started such that, you know, after time t star, it just evolves according to these transition dynamics. And that's what this equation here says, right? That if I start at t star and then, you know, I somehow get to time s and position x and then let it evolve to time t, then it's just the same as, you know, my recipe for where I should be at time t starting from t star, right? And so the Bessel 0 guy has a very nice entrance law. You can write down explicitly what the transition density function is for the Bessel 0 process. It's something that involves, surprise, surprise, Bessel functions. That's why it's called the Bessel 0 process. And, you know, in some nice 19th century mathematics. And if you just use the asymptotic behavior of the Bessel function as the argument goes to 0, you end up seeing that this object here is an entrance law for the entrance time t star, right? So this is a way of getting our process away from 0 and then it, you know, letting it evolve like that, like the Bessel 0 guy thereafter. Okay, so now the thing about this is that the entrance law doesn't define a probability measure on path space. It defines a measure with, you know, infinite total mass, because, you know, what we have to do is, you know, to get the thing away from 0, well, you know, if we've got paths away from 0, you know, starting at 0, they really want to go stay at 0, right? So there's this sort of thing that we have to, put more and more mass at, tiny little paths that just wink into existence and then wink out of existence straight away. But we can build this, infinite measure on, on path space that, has its finite dimensional distributions given by the recipe that you'd think that, somehow magically we get to position x1 at time s1 that's bigger than the time that everything starts, and then after that the dynamics adjust, the Bessel zero dynamics. Okay, and now we can do exactly the same thing with Wright-Fisher. We can force Wright-Fisher to get away from 0 by, remembering this is the distribution of Wright-Fisher that starts at position x at time t star and has, of course, the selection and dominance parameters alpha and h. And then this is our new candidate for the reference measure, the Bessel zero guy. And we always have this as the density of the Wright-Fisher against the Bessel zero guy. It's always of this form. And so remember, this now is our reference guy, the Bessel zero, that's, forced to get away from 0, and then we just, whack in, the obvious density that, is, from here the correct one to use, because, we always had this density no matter what the starting point x is, and, this defines now a dynamic for the Wright-Fisher process that's getting it away from 0 and then evolving thereafter as it should. Okay, now the way I sort of define things there, this object is an infinite measure on path space that is defined on paths that just are indexed from time t star onwards, but of course we can think of that as a measure on paths indexed by the whole of the real line by just setting the paths to be 0 up to this time t star when the path's forced to get away from 0. And so now we've sort of gone through a lot of kind of convolutions, but we're sort of finally at the point of defining what our prior should be on the allele frequency path. It's going to be an improper prior. Okay, so when I say conditional, these scalar parameters, we're just going to if we sort of just for the moment condition on them, then the part of the prior that describes the time and space transformed allele frequency path is just going to be this guy here, right? So this is saying, we're forcing ourselves to get away from 0 at this time here, right? Now, T0 is in, calendar time, the time that the allele arose. But after we've done the time change, this is the time that's the time and space rescaled Wright-Fisher is actually leaving 0. And, of course, we have to use the dynamics that have the appropriate selection and dominance parameters.
Wait,
Yeah.
You're actually forcing it to get away from 0 at T0 or just like sometime after T0?
Well, it's at 0 at T0 or FT0, and then straight away after that it leaves, right? So you're forcing it to do something kind of lewd and unnatural, but that's why it has to be a an infinite measure, right?
But I mean, also just you'd expect that, okay, you saw it at 0 at t0. It was actually 0 for some time after that, and then sometime before the next.
No, t0 is by definition the time that it gets away from 0. Yeah, it's not. Yes, it's probably notation that we should change. Yeah, t0 is the allele age, whereas the t1, t2, they're the sample times. I'm amazed that you. T star was just because ft0 is. I didn't want to use t0 because, the thing that I'm going to plug in here is ft0. So, this is the time when everything gets going, right? And so the time that everything gets going for the actual allele frequency path is t0, but after we've done the transformation, the time that everything gets going for the transformed path is ft0. Yeah, it's quite a lot of stuff. Yeah.
So given that you observe the frequency at a later point in time,
Right.
wouldn't you also want to condition on that frequency?
Right. So that's exactly a good point. That ideally one would like to have that. What we were taking is not the Wright-Fisher measure sort of done like this, but in fact Wright-Fisher that is, in a sense, conditioned to start at 0 and be between 0 and 1, at the present day, right? And similarly as the reference measure to use something like Bessel 0 that's conditioned to do the same thing. Okay. The problem with that is that there's sort of you're back to sort of needing to solve the PDE to get the kind of denominators in that conditioning, right? You need to know, what's essentially the probability that this of probability distribution of kind of where you are at the end. And so this, I was sort of going to sort of say this, but you kind of, forced me to say it now, is, just, doesn't completely catch that thing. It's going to be something that's distributionally very close to that, because, in a sense, what we're doing is conditioning the Wright-Fisher to get away from 0, right? I mean, that doesn't make sense in terms of giving you a probability measure. It gives you something that's one of these infinite measures, right? This infinite measure really is Wright-Fisher conditioned to get away from 0 for, some positive time, so the conditioning's slightly different to what you'd want, but the fact that we're then got data that's telling us that the allele frequency is strictly positive at all various sample times is kind of going to be throwing away the paths that correspond to the process just winking into existence and then winking out. So the conditioning that we really want to have there is to some extent forced to happen by us using the data to tell us that even though the prior puts mass on paths that come into existence and then die, the data tells us that they can't be ones that are relevant to our problem. Okay, and so then of course we've got to have 5 minutes, right? Yeah. So then we've got to have sort of priors on the selection coefficient and the dominance coefficient, and just take whatever your favorite kind of prior is for scalars. Then we also need a prior on the allele age, and there's good reasons for using the improper prior that has its density, against Lebesgue measure as just being the relative population size at time t. So, in times when the population size is greater, you're more likely to be seeing the allele arise there. And then, just multiply all your priors together to get, a marginal prior on these three scalar parameters. And then, of course, on the previous slide, we described what the conditional prior is on the path, given the scalar parameters, and so we've given a complete specification of the full prior on the time that the allele arose, the selection and dominance coefficients, and the allele frequency path. Okay, and so, here's sort of then how you're going to implement sort of Metropolis Hastings, and the thing is that we've got to have some, proposal mechanism for getting ourselves around path space, right? Some way of, taking a path and, proposing a new path, and, what we've got to do is, how are you going to sort of propose a new path? Well, you just pick a little interval, and then the piece of path between those two time points, you're just going to update it, and you're going to, the proposal is going to be, drawn according to the distribution of a so-called Bessel bridge, right? So a Bessel zero process that's conditioned to, start at the beginning of the interval, where the previous bit of path started, end at the end of that interval at the place where the previous bit of path started, and then, follow the Bessel zero dynamics in between that. And this is sort of easy to simulate one of these bridges, so easy to do a proposal, in terms of another nice little bit of stochastic analysis, which, looking at Nick, I don't have time for. It's a sort of a fascinating but non-obvious fact that bridges for a Bessel zero process, which is this sort of rather mysterious thing, right? Because, the Bessels with positive integer dimensions had something to do with Brownian motions, radial parts of Brownian motions, whereas this zero-dimensional guy, what's it? Well, bridges of this guy are the same as bridges of a Bessel 4 process. So you can simulate these things just by simulating bridges of Bessel 4s. And, in order to do that, you've got to do a little bit of stuff worrying about, radial parts of Brownian motion and things like that. And so you've got to do things with von Mises-Fisher distributions and things, but it's not that hard to do. And so that's, a bit of path in the middle. How do we update it? Well, the updates of the allele age are similar. We do something, we want to update from here to here for the allele age. Well, we've just got to build a Bessel zero bridge from here to here, which is the same as a Bessel 4 bridge. And, the proposal ratio needs to account for the appropriate densities of the paths that do this thing. And similarly, the final bit of path, the updating of that is just a similar type of idea. And, here's just a picture of, what an update looks like in the middle of the path, at the start of the path, and at the end of the path, just like I described on the three previous slides. And so let's just look at a particular example for the ASIP locus in horses. So, the data is these 1, 2, 3, 4, 5, 6 dots. And, what we have here is that the black line is the median of the posterior distribution at each point in time of the allele frequency path. The red guys are the upper and lower quartiles, and so the green guys, they're the 95th percentile and 5th percentiles. And so then, here's the posterior of the allele age, right? Obviously, the allele age is going to be concentrated at times prior to when you started seeing positive frequency in your samples, but it tails off, really quickly. And here's the prior for the alpha parameter and its posterior. Marginal posterior, and it's hard to see the dotted guy as the prior for the dominance parameter, and the solid guy is the posterior. And here's the joint posterior for the two parameters dealing with selection. So you see that it's looking like the dominance parameter is positive, and also the alpha, the selection parameter is positive. And in fact the most likely values of those parameters are the following. So you're in this over dominance situation, and so that leads to these posterior distributions on the trajectories, quickly rising and then kind of leveling out, right? It sort of meshes with that quite well. And so just some acknowledgements, to people that particularly Josh has talked to down in Valley Life Sciences, and just some of the papers that got mentioned there and sort of what they're about, and just some of this stuff about Wright-Fisher bridges is a paper with Josh, Bob Griffiths and myself, and Josh also has a really nice paper on thinking about Wright-Fisher in the world of, sort of path integrals, sort of a little, a nice sort of variant on the usual kind of stochastic calculus kind of way of thinking about things. Okay, thanks very much.
Hey, I think one quick question.
Yeah, sorry. Did I go?
Why are horses homogeneously mixing across the planet?
Yeah, right. I mean, that's of course exactly the sort of issue, right? And that sort of all of these things of assume that you're dealing with a panmictic population, and
But you must have some story for why this doesn't change your estimate.
No, I mean it's just well, of course, one would then need to start talking about of course what goes into here is just the usual sort of boilerplate about effective population sizes, and that Wright-Fisher still works as long as you put in n sub e instead of n, et cetera, right? So that's and of course there are rigorous results that establish that, but it is a leap of faith for sure.
And horses can run.
Yeah.
So, if it's too long, we can take it offline later. But at the most basic level, a lot of your stuff reminds me of the stuff that Anthony Edwards used to do with random genetic drifts on the surface of a sphere. And,
Right.
But a lot of that but it never solved the problem what you did when you got to the edges of the orthant. So I wondered how much of your machinery is really because you're worried about this zero frequency, what happens at the boundary, and how.
That's, I mean, that requires, a lot of extra, kind of worrying to sort of do that, to handle this, that you're not just dealing with, Wright Fisher, you're dealing with Wright Fisher conditioned on an event of zero probability. And so, this thing, the condition guy, magically gets away from zero, but from there on, it's going to have a distribution that's absolutely continuous with respect to that of, the unconditioned Wright Fisher. And so, it's sort of going okay.
And the other thing was that we're doing problems with continuous time Markov chain, trying to do NCMC.
Yeah.
And Vladimir Minin, who's done a lot of that work, has got some really nice results where you can do NCMC by augmenting the process. So then you have a process that you can sample from.
Well, that's what we did here. I mean, putting the path in is exactly that augmentation idea, right? That
it's a much more complicated one than the sorts of augmentation he seems to be using.
Yeah, but this is the sort of thing that people in the signal processing community and stuff like that, when they talk about data augmentation, it's essentially that instead of thinking that you've just sampled the signal, that you've seen the whole signal.
But in order to sample from that continuous process, he's augmenting that process. So it's not just data augmentation by putting in the path, it's by putting in additional events into that underlying continuous process that you want to try and sample from.
Okay.
And which enables you to sample from inhomogeneous processes and so on.
Yeah, that might be.
And I don't know if that has...
Yeah, no, that might actually be relevant, yeah. Thanks, Elizabeth.
Let's hope that can be solved over tea.
Thanks.
Keep on time.